Okay, we are in the middle of discussing the multiple linear regression model. So far we've defined the model, we have done our estimation, and we have looked at inference for the parameters. So today we're going to continue that discussion. First, let's recall what we have so far. So we have a random vector of our response variables, and so we're expressing that as a deterministic linear component, where X is the matrix consisting of the predictors in its columns, and then beta is the vector of parameters we've estimated, and then plus, so this is the deterministic part, we're estimating beta, and then we have the random part, which accounts for any unexplained variability that the model does not capture. Okay, and so we learned, okay, so this entire expression by assumption has a multivariate normal distribution. The mean is x beta, okay, so this linear part models the mean response. And then the independent and identically distributed errors all have variance sigma, so it can be written compactly in matrix form, sigma squared times the identity. Okay, so we also learned that the parameter estimates, okay, so it's a vector, so I write beta vector, so the estimate of that, we learned it can be written as x transpose x inverse x transpose times y. Okay, and so that's our parameter estimates, and then we have our fitted value. So this is mu hat. Okay, so then x beta is the mean, and our estimate of that is x times beta hat. And then we have our residuals, so that we call that these are vector residuals. E is the difference between y and the fitted mean mu hat. Okay, so we defined all those notations last time, so let's just call this. So this is the estimates. This is the fitted value, and then these are the residuals. Okay, and so we've done the linear algebra for that. So I would like to take a few minutes to talk about a geometric interpretation of what we've done, especially to put it into in terms of linear algebra terms. So I think this will give us an equivalent way of thinking through like what these quantities mean in terms of geometric picture. Okay, so let's take a little rabbit trail and let's talk about geometric interpretation. And specifically, we're talking about the data and how we visualize that. So let's give that sidebar. Okay, so remember we can write the matrix X here written in terms of a bunch of column vectors, each one corresponding to the first one, the intercept, and then each of the other columns corresponding to the p explanatory variables. Okay, so we've seen this matrix representation before. So we have a vector of ones, and then we have the first predictor, x1, and then up to xp. Okay, so remember this one is we assume we have n observations, so this is an n by p plus 1 matrix. Okay, so these are remember, this is a vector of constants, and this is the information we have for which to fit a model for y. Okay, so we can think of y, the vector of y. So I'm thinking of this as the data we actually have. So I'm going to write lowercase y here. So what is y? Well, y is, okay, so we know it consists of a vector y1, y2 up to yn. Okay, so those are recorded values for our responses for n observations, and so we know that this is a vector in our n. Okay, it's an n-dimensional vector. So these are the so let's call this the values of the responses. Okay, so all right, so a linear algebra term is span. Okay, so let's recall that together. So okay, so here I have a bunch of vectors. Okay, so they're expressed in column form. So we can look at their span. Okay, span of the x here. Okay, so in other words, what to remind you, span is all possible linear combinations of its columns. Okay, so you can think of this as linear combinations. So let's define some constants. It's called like b0 times first column, and then you have you add linear combinations of b1 of the x1 column, and so on, and then you'll be up to bp times xp column. Okay, so the span is all possible linear combinations of these p plus 1 columns. Okay, so these b's, so b0 up to bp, all of these are real numbers. Okay, where so this is all linear combinations of the columns of x. Okay, so this is the set of vectors represented by the span. Okay, and so well, what is this? Well, this is a subspace of Rn. Okay, so each of these is a vector of dimension n, and so this linear combination is also in Rn. Okay, so this is specifically a subspace of n-dimensional Euclidean space. So let's also remember that by the way we set up x, we set up our explanatory variables such that all the columns are linearly independent. Okay, that's one assumption we stated at the beginning of multiple linear regression, and recall. So let's recall that. So recall by assumption the rank of the matrix X is p plus 1. Okay, and so so writing it in this way gives us a little bit of insight about how we should set up our explanatory variables. Okay, so why can we always assume that we have a full rank matrix? Well, if X is not full rank, it means at least one column is linear dependent on the other. So for example, you could write XP in terms of maybe XP is like X1 plus X2. So that would be an example of a linear dependent variable. And so we look at it in terms of the span of the vectors making up this X matrix. So you notice if you have a linearly dependent column, it's not going to add anything to the span of the matrix. Okay, so in other words, the set of possible predictions you can make using those X's, you don't gain anything by adding linearly dependent columns. It doesn't change the span. Okay, and so therefore that's why when we set up our regression, we can ditch any of the X's that are linearly dependent, or in other words, can be written as a linear combination of the others. Okay, so therefore, since we have control over how we set up this X matrix, we can always define it to be full rank. Okay, so that is practical implication. Later, we're going to talk about, well, what happens when you have X's that are very correlated with each other. Well, later we talk about collinearity, and we will discuss ways of addressing that. And indeed, having highly correlated X's is generally not a desirable property because they carry much redundant information. Ideally, we would say the X's are, in the ideal case, they might even be orthogonal to each other. Okay, but we will come back to the point of collinearity later. Okay, so all right, so back to interpreting this this subspace or the span of the matrix X. So what is it? So what does it represent? So this span, okay, we can say it represents all possible values, all possible. Well, in this case, they're vectors, vector values, X, B. Okay, so we're defining here B is these numbers B0 up to B P. Okay, and the reason I write it like that is now you start to see some resemblance with this whole multiple linear regression model setup, because we're assuming in our model that the mean response is X times beta, where beta is an unknown set of parameters. Okay, and so what we're saying here is the span of the matrix X is in fact all possible values that you could get for X times a vector of constants. Okay, and so there's two specific values of B that are most important to us. Well, one is our parameter estimate, so that's going to be beta hat, and then there's also the unknown underlying true, so-called true beta. Okay, and so we should also point out then that y, okay, so the reason we do modeling here, and the reason we set up a random error here, epsilon, is because generally we don't expect y, so generally the values of the responses y is not going to be in the span. Okay, well, why is that? Well, if it were, then that means y would simply be exactly a linear combination of the x's, and there would be no. That means this linear model on x would perfectly explain y. So generally, that's not the case. That's why we do. That's why we fit. That's why we do least squares and fit the betas. Okay, so generally, y is outside of the span, and so we fit the model. So since the linear model is an approximation, and so we have epsilon represents variability not explained by the model. Okay, so now we can put everything together as a picture, and we can see in this sense why our least squares estimates are sensible. Okay, so let me do this more. Okay, so intuitively then, okay, so since y is not in the span, well, let's find the closest points in the span to y, and that would intuitively be a sensible way of choosing this vector b. Okay, so intuitively it makes sense to choose an estimate. Okay, so I'm talking about estimates, so I'm going to call it beta hat, because as you might expect, this is going to correspond to our least squares estimate. So that okay, so then the x beta hat is close to y. Is as close to y as possible. Okay, and so let's draw a picture to illustrate this. Okay, so let's call this. So let's call this guy the span of x. So this is a subspace, and so the reason we model is because, well, the value of y, so this the responses are not going to be captured in the span, so it's outside of the span, and so we have, and somewhere. So in our modeling framework, well, somewhere in here we have x beta. Okay, so if we imagine there was a true model and a true value of beta, it would lie somewhere in the span. Now, intuitively, well, so where would we choose? Where on the span would it be closest to this to the vector of responses y? Okay, so that's what we're going to call x beta hat. Okay, and so the reason I draw it this way is, well, now you have this vector difference. Okay, and so what's our term for this vector difference? Well, this is the residual. Okay, so this difference is between the responses and the fitted values. Okay, so the fitted values lie on the span. Okay, and the residual vector captures the difference. It's the vector difference between the responses and the fitted value. Okay, so what does it mean in linear algebra to be closest? Well, what's going to be the property then of this difference vector E? Well, it has to be orthogonal to this subspace. Okay, and so we can put. So let's put. So the closest is the orthogonal vector to the subspace. Okay, so what does that mean in terms of, so that's pretty intuitive. So just to recap what we've said so far, okay, so all the possible x betas are captured in the span, okay, and then the responses are outside, okay, so we ask, well, how can we get the closest? Well, the closest would be such that this vector of residuals, E, is orthogonal to the span. Okay, so what does that mean? Okay, so let's write out the consequence of this. So that means E must be orthogonal to the span of X, which, as we know, means that it is orthogonal to all the columns of X. Okay, so what does it mean when E is orthogonal to all the columns of X? Well, what does orthogonal mean? It means the dot product between E and each column of X is 0. Okay, so let's write down what that looks like. Okay, so the first column of X is the vector of 1s, so 1 transpose times E. Okay, so I'm going to write out what E is, so it's clear. So Y minus, so X beta hat, we called mu hat. So that's shorthand. Okay, so that's 0. And in the next column you have X1 transpose Y minus X beta hat. Okay, and then that's going to be true for all of the predictors. Okay, so this is what the orthogonality condition would mean. Okay, and so now you look at this, and hopefully it looks a little familiar to us, because what are these? So this is, in fact, it's equivalent, these equations, so now you have p plus 1 orthogonality conditions, and these are in fact equivalent to the p plus 1 least squares equations that we had when we were solving the least squares estimates of beta. Okay, so that's the connection to what we've done so far. So these are the same as the least squares equations. Okay, so the beta hat that satisfies the least squares equations also satisfies this orthogonality condition, which comes quite intuitively from a geometric viewpoint of finding the closest point in the span to the response vector y. Okay, so I think that's helpful in a couple of senses. Well, first we see another way of getting the same beta estimates, and also we review a little more of some linear algebra terminology, and we get a nice picture of what we're actually doing when we're calculating the estimate beta hat. So clearly then the beta hat you get out of this is exactly the same beta hat we get out of the least squares estimates. So if we solve these equations, we get x transpose x inverse x transpose y. Okay, so with that in mind, let's think of let's take a closer look at the fitted values, and let's see how a prediction looks like in the multiple linear regression context. Okay, so again, let's write down some key relationships. So mu hat is x beta hat, and then we have the vector of residuals is y minus mu hat. Okay, and so we're going to introduce one more matrix because it'll be helpful as we do prediction, and that's called the hat matrix. Okay, so I'm going to define the so-called hat matrix, which is denote by H. Okay, so it looks like this. It's X times X transpose X inverse X transpose. Okay, and so why is that useful? Okay, so let's see how it relates to the fitted values and the residual. But before I do that, let's look at a couple of properties. Okay, so side note, properties of H. Okay, first one is it is symmetric. Okay, so H is symmetric. Okay, so let's check that. So symmetric again means that H transpose equals H. Okay, so let's just check that. Okay, so what is H transpose? Okay, so we have to take the transpose of everything in here. X transpose X inverse. Okay, and so as we know, the transpose operation means we take the transpose everything inside, but in the reverse order. Okay, so we have X transpose transpose, so we have X, and then in the middle you have this guy, X transpose X inverse, but then we already learned that this is X transpose X is symmetric, and so therefore transposing doesn't do anything, and so in that indeed we get that H transpose is just itself, because the last term is just X transpose, so that's H. Okay, so that's one property of this hat matrix. And the other one is, again, we'll review one other term. H is idempotent. Okay, and that means that if you multiply H by itself, you just get H back. Okay, so again, let's verify this property as well. Okay, so let's just do the multiplication. So H times H is X. Okay, so I'm going to write H 2 times. Okay, and then I'm going to group this X transpose X so that I cancel one of them, and so we see what's left over after canceling one is simply get H back. Okay, so this hat matrix has these two properties, and we can easily verify. And we can verify. So if I take the identity minus H, is also symmetric and idempotent. Okay, so the reason for defining this H matrix is that we can now, in fact, write both the fitted values and the residuals quite neatly in terms of H, and these properties will help us as we derive the corresponding estimators. Okay, so we're going to follow. So for the rest of today, we're going to follow a very similar pattern to the lecture where we did prediction for simple linear regression. We're just now going to do it in the multiple linear regression context. And I've just defined some notation to make that a little easier. Okay, so I'm going to use these facts and derive the corresponding estimators for these, viewing them as random vectors. Okay, so all right. So now let's view mu hat and the residuals as random vectors. Okay, so what can we say about them as random vectors? Well, okay, so let's first write write this guy. So mu hat. Okay, so as we said, it's x beta hat. Okay, so let's plug in beta hat. So that's x. Okay, so what is beta hat? So beta hat, we write it out as x transpose x inverse x transpose y. Okay, so now that we've written it out, we see that the way we define the hat matrix is very convenient because this entire thing in front of the y is the hat matrix that we've just defined. Okay, so the fitted values, in fact, is the hat matrix times y. Okay, so that gives us intuition for why we call it the hat matrix. Because what does it do? Well, it takes the random. So the random vector y is multivariate normal, and then h is in terms of the x's. So it's a matrix of constants. So hy is simply a linear transformation of the random vector y. And what does this linear transformation do? Well, it maps y, so it transforms y to give us its fitted values. Okay, so it gives us the mu hat. Okay, so that's why it's colloquially called the hat matrix. It maps y to its fitted values. So that's what h does as a matrix of constants. Okay, and then in a similar way, let's write E. So what is E? E, the residual vector is, so we view it as a random vector, so I'm going to change the y capital here, y minus mu hat. Okay, so we already wrote that it is, mu hat can be written as h times y. Okay, and so I want to factor out y. So we can of course insert an identity here without changing anything, and so therefore the residuals can be written as identity minus the hat matrix times random vector y. Okay, and that's helpful because now we can get our mean and variance of these two random vectors in terms of the hat matrix and in terms of the covariance matrix of y. Okay, so let's do that next. So first, let's do to demonstrate. Okay, let's do expectation of the fitted values. Okay, so this is expectation of hy. So we can factor out the h, do e of y, and what is the model mean for y? Well, that is simply x beta. Okay, so let's simplify. Okay, so h is x transpose x inverse x transpose, and then what is e of y? E of y is x beta. That's our multiple linear regression model. Okay, and so this part is e of y. By the way, we set the model, and then now we see that again we have a nice simplification here. So this x transpose x cancels. Okay, so this simplifies to x beta. Okay, and so in other words, the viewing the fitted values as a random variable, its mean is in fact the mean of our multiple linear regression model, x beta. Okay, and we can also do its variance. Okay, so we do variance of h, y, and so again we use what we learned about random vectors. So this is h variance y, and then h transpose. Okay, and so let's plug in variance of y. So h sigma squared identity, because all the errors are ID. Variance sigma squared, so plug in that. That's covariance matrix of y, and then h transpose. Okay, and then this is where the properties of h are very helpful. So we don't have to actually write out everything, because identity, so we can, that doesn't change anything. Sigma squared we can pull outside, so you have sigma squared times h times h transpose, but then h is symmetric, so it's just h times h. Okay, but then h is idempotent, and so h times h is just h. Okay, so this just simplifies to sigma squared times the Ham matrix. Okay, so that's why we derived these properties beforehand. We're going to apply them directly here. And we'll do the same now for the vector of residuals. So we have E of residuals, E residual vector. Okay, and so let me take the expectation of this. So E of y minus E of h y. Okay, and we've done all these already, so this one is x beta by the model, and then we already derived hat matrix times y, because that is the fitted value. So we already derived that's x beta, so this is 0. Okay, so why does that make sense? So on average, the average of the residual expected value is 0. Makes sense. Okay, so in other words, it's just the flip side of what we derived here. So the fitted value on average correctly predicts the mean, the model mean, and so the average residual is 0. Okay, and then variance. Okay, so variance, so we have I minus h, variance y, then I minus h transpose. Okay, and then it's very similar to variance of the fitted values, so this is sigma squared I, so we have sigma squared I minus h transpose. And I said here we can verify that I minus h also is symmetric and idempotent. So by that fact, this is simply sigma squared I minus h. Okay, so we have now the mean and variance of these random vectors. And so the last part is, well, what distribution do they have? And so what we have to, so what we see here is, well, what kind of distribution do they have? Well, mu hat is a linear transformation of y, and likewise the residual is also a linear transformation of y, and y is multivariate normal, and so therefore not only are mu and e having these means and variances, they are also multivariate normal with those means and variances. Okay, so since both mu and e, the residuals are linear transformations of y, we have that they're multivariate normal. Okay, so therefore, mu hat is multivariate normal, mean is x beta, variance sigma squared times the hat matrix, and the residuals viewed as a random vector is also multivariate normal, mean 0, and variance covariance matrix sigma squared times identity minus hat matrix. Okay, so with that in mind, we are ready to do the last part of today, which is to derive the prediction intervals, just like we did for simple linear regression. So consider now prediction. Okay, so suppose we want to predict the value of the response for, okay, so we're going to define a set of x's. Okay, so we're going to now input, in order to use our model, we have to input a vector of x's, so those are the p explanatory variables associated with the response we want to predict. So we can write that as a vector, so let's call it x naught vector. Okay, so what do we need to put in this vector? Well, we need to put all the values of the p explanatory variables, and for the sake of notational ease, we're also going to put a 1 at the beginning, and you'll see why in just a second, because it makes prediction possible to be written as simply in terms of vector multiplications. Okay, we'll put a 1, so that's going to represent the intercept. And then we're going to put the values of x for which we want to predict y. So there's p of them. So x. So these are the values we're going to put into the model: x0, 1, x0, 2, up to x0p. Okay, so this is our p1. So this is a 1 by p plus 1 row vector. Okay, so putting the 1 explicitly for the intercept means we can just do everything nicely in terms of vectors. So let y0 be the random variable representing the response associated with this new set of x's. So the vector x0. So the multiple linear regression model says that y0 would be normally distributed. Okay, well, what is, so, okay, let's write it in full first. So beta 0 plus beta 1 x0 1 plus up to beta p x0p. Okay, and then variance sigma squared. Okay, so that's what the model says. Okay, and so our prediction. So we would predict. Okay, so our prediction would be the value. Okay, so let's call it y0 hat. So this is the one we can calculate based on our fitted model. So what we do, well, we have estimates for all the beta. So we plug everything in. So this is beta 0 hat plus beta 1 hat x01, and same for each of the p predictors, beta p hat x0p. Okay, so that's the sensible value to predict. And notice by writing the entire x0 vector in this form, we notice this is simply the dot product between the vector x0 and the vector of beta hats. Okay, so this x0 vector times beta hat. Okay, so that's why we defined the notation this way. Okay, so what does this thing represent? So this, well, is the would be the fitted mean associated with this distribution. Okay, so let me say this thing represents the estimated mean response for mean response given the values of the explanatory variables given x01, x02 up to x0p. Okay, so for that, for the specific values of our predictors that were given here, then y0 hat represents the estimate of the mean for those values of x. Okay, and so that's the value we can calculate, and so again we can look at its distribution by viewing it as a random variable. Okay, and so that's the value and corresponding distribution as, okay, so we're going to take the expected value again, so E of y0 hat. Okay, so this would be x0 times the expectation of beta hat, which we showed last time is an unbiased estimator for each individual beta in the vector, so x0 times beta. Okay, and so this, not surprisingly, on average, we get the true model mean, which is vector x0 times beta. Okay, so this is the same as this thing. Okay, so these are equal. Okay, and so we have that it's an unbiased estimator for that mean based on the multiple linear regression, and then its variance. Okay, so we've done quite a few of these kinds of variance calculations now involving expressions based on matrices and vectors. So y0 hat x0 times beta hat, so we have x, and x0 is a row vector, so this is x0 variance beta hat, and then x0 transpose. And what is the variance of the vector beta hat? Well, we derived last time is x transpose x inverse, so we can plug that in. And again, we can say that y0 hat is a linear, can be expressed as a linear transformation on y's, which are multivariate normal, so this is a normal distribution. And so y0 has normal, mean is x0 beta, and then variance I think I missed a sigma squared here, so let's fix this first. So variance beta hat has a sigma squared in there, so put that back in first. Write this. Okay, that's better. All right, so put the sigma squared back in for the variance, because that's the expression we got last time. Okay, so back to normal distribution for y0 hat. Thank you. So we have, okay, so write the sigma squared first, and then x0 transpose x inverse x0 transpose, x0 without transpose, and then x0 transpose. Okay, there we go. All right, so that's the normal for our prediction. And so okay, so we can do our usual things with normal. So we could do, for example, y0 hat minus, so subtract out its mean, and then divide by the standard deviation. Okay, so I'll get it right this time. So sigma, and then inside the square root is x0, and then x transpose x, x0 transpose. Okay, so this is the standardized form for it. And okay, so again, we don't have sigma, so we have to estimate it. So once you put on a hat, okay, so same thing but with sigma estimated. Is going to have a t distribution. Okay, and so let's remind ourselves of degrees of freedom. So it'd be the number of observations and minus the number of model parameters. And the number of model parameters is p plus 1, because we estimated beta 0 and then beta 1 up to beta p. P plus 1. Okay, so that relationship holds for multiple linear regression as well. Let's plug in the estimate for sigma, and normal becomes a t with the corresponding residual degrees of freedom. Okay, so what this means is we can use it to make a confidence interval. Okay, so therefore, a 1 minus alpha confidence interval for Okay, so let's state carefully what this distribution could be used to construct a confidence interval for. So what did we just estimate? Well, we're predicting trying to predict the new value. So we've started by stating this this prediction y0 hat, which is really the estimated mean response. Okay, so we use this t distribution will give us a confidence interval for the mean response. Okay, so let's state that carefully. So for the mean response given x0. Okay, so we use our usual technique. So we take y0 hat plus minus constant c, which is going to be from the t distribution with n minus p. So there's p plus 1 parameters, n minus p plus 1 degrees of freedom. Okay, and then we're going to put the standard error. Okay, so that's this whole thing. So sigma hat x0 x transpose x inverse x0 transpose. Okay, so that's a confidence interval where C is the 1 minus alpha over 2 quantile of a t distribution with n minus p minus 1 degrees of freedom. Okay, so that's confidence interval for the mean response. Okay, so we're almost there. We just now need to do something pretty similar to what we did for simple linear regression to get the prediction interval. And the reason I'm writing it separately is I want to emphasize that this confidence interval for the mean response is different from the prediction interval for the value y0. Okay, so we'll keep this one in mind because we're going to compare that with the corresponding prediction interval in just a moment. Okay, so we'll follow a very similar procedure as for simple linear regression by defining a prediction error. Okay, so this is quite analogous to what we did that time. So y0 minus y0 hat captures prediction. So there's a question, shouldn't the denominator be sigma divided by root of that? So the normal is sigma squared times all of this. And so therefore the denominator is the square root of all of this, so this line is correct, and then we divide, and then we change sigma to sigma hat to get the t distribution. So I believe my expression on the board is correct. And then this thing in the denominator is therefore the standard error of the predictor, y0 hat, and so therefore confidence interval is the value, so y0 hat plus quantile times the standard error of the predictor. So I believe this expression is correct. Okay, so prediction error is the difference then between y0 and the predicted one, y0 hat. Okay, so very similar to when we did simple linear regression. We observed that these two are independent. Okay, and these are independent because y0 is a random variable with variance sigma squared. Okay, and then these ones are in terms of y1 up to yn. Okay, so y0, so all the y's are independent, and so all these, so both terms here are independent, just like in the simple linear regression case. Okay, so this guy, remember, is a function of y1 up to yn. Okay, so everything in here is independent, and they're all normally distributed. So we know that this is going to be normal as well. Okay, and then we just need to find what this mean and variance is. So let's do that. So expectation y0 minus y0 hat. Okay, so again, by construction, this is x beta, and then we already found the expectation of y0 hat. I'm sorry, this is x y0 corresponding to the predictor. So x0, the values of x for which we're predicting. So x0 times beta, and then the mean of y0 hat we already derived. It's x0 beta. So just like in simple linear regression, this is the average prediction error is 0. Okay, and then variance, y0 minus y0 hat. So analogously, these two are independent, so we can just add up the variances, y0 and then plus minus 1 squared, variance y0 hat. Okay, and we have derived all of these already. So variance y0 by the model is the residual part, so it's sigma squared, and then variance of y0 hat we already derived here. So it's sigma squared times this entire expression. Okay, we'll leave that here for a moment because I'm going to compare in just a sec. Okay, so therefore, we have shown that y0, so the prediction error has a normal distribution. Mean 0 and variance is sigma squared, so it's factor of sigma squared, so 1 plus x0, and so this entire expression again. Okay, and so we can do a similar thing. You can standardize and get a t distribution of it. And so analogously, we get our prediction interval. So a 1 minus alpha prediction interval. For what we would observe, we got to measure y for this set of predictors, so that's y0. Okay, so analogously we have y0 hat plus minus the same constant. And then now, okay, so I didn't write out the standardization, but you can see this, it'll be the square root of this expression and then with sigma replaced by its estimate. Okay, so we have sigma hat root 1 plus, and then everything else that we saw already. Okay, and then same C, so I don't need to redefine C, it's the same guy. Okay, and so I think the last point is to compare these two expressions. So this one is a confidence interval for the mean response given x0, and then this one is a prediction interval for y given x0. So you notice these are slightly different. fact. So the difference is that the prediction interval is wider. Wider than this confidence interval for the mean. Okay, and we see that because there's this extra 1 plus term here. Okay, so this is strictly wider than this confidence interval over here. Everything else is the same. Okay, so why does that make sense? Well, here we're trying to estimate the mean, and here we're trying to estimate a particular value. Okay, and so intuitively it's easier. So I'm going to write it this way. So estimating an average, and this is true in general. I mean, it's quite intuitive. Estimating the average is easier. Okay, I'll put easier in quotes because I'm just using it colloquially. It's easier than an individual response. Okay, so this one represents hypothetically, if I had like 100 new people and I want with all the same values of x, and I want to estimate what's the average of those 100, then that's what the mean response confidence interval would represent. So intuitively, it's, for example, easier to estimate the average of 100 responses than to estimate the value of an individual response within that 100. So that's why you see there's this difference between these two expressions. Okay, so now we have completed how to do prediction for multiple linear regression. So let me just end by seeing if there are any other questions in chat. Okay, so there's one question about the expectation of mu hat. So this is probably from earlier. Okay, I don't see the question anymore, so I guess that was probably clarified earlier. Okay, and then there's another one. When do you use confidence interval instead of prediction interval? Okay, so the confidence interval is if you want to estimate the average. So if you imagine hypothetically, right? Let's say you have values for x, and you have a lot of people with those x values. The confidence interval would give us the estimate of the average of everyone, hypothetically, who has that set of x values. And so therefore, this confidence interval is narrower than when we try to estimate the value of the response for one individual who has those set of x values. Okay, so there's another question. How is the expectation of mu hat equal to x beta? Okay, so that's not on here anymore, so let me make a little room here. So we need to do the expectation of mu hat. So that's E. So that's this expression. Okay, and mu hat is expectation of x beta hat. That's definition. So that's x times E of beta hat. And so E of beta hat is beta. Okay, because beta is an unbiased estimator. So this part is from last lecture. Okay, any other questions? Pause for a few more seconds. Okay, so it looks like we're good for now. So we'll end today here, and we'll be back on the stream on Wednesday.